Welcome back. We're in file 2. This is a file dealing with risk measures. We're going to look at risk measures of stocks individually and then how much they have risk in common. So we're going to look at a variety of risk measures, and let's start with looking at the variety we're going to have. We're going to talk about calculating average. We're going to calculate variance and standard deviation. We'd like to know, given the average and the standard deviation, which security might be more attractive, so we use a measure called coefficient of variation. Then we'll look at risks in common between two stocks. This is covariance, also measured by correlation. And then if we're looking at a stock relative to a stock index, we call that beta. So I'm going to start with made-up data, and we're just going to be talking about calculating using made-up data. So we're going to talk about the mean. The mean is the average of something. In statistics, we call it mean. And if we take the past average and say we think that's going to continue to happen in the future, we call it expected return. We're going to use the holding period return calculation that you saw in file 1 at the end. So we're looking at what is the return for January. Well, it's the price change over the month of January, which would be the February 1st price minus January's first price, and then you divide by January 1st price. You'll see I have no dividend in the story, so it's just a percentage change in price. Look at stock A, $27.50 minus $25 over $25, which would be 10%. $29.15 minus $27.50 over $27.50 is 6%, and so on. So if I take those four numbers, 10, 6, 7.99%, and 10, add them up, divide by 4, I get the average, which is 4.5%. We'll call that the mean return, or in the future, the expected return. I've given you data for holding periods for a company B and for an index. You can see the respective data for the 4 time periods, January, February, March, and April. And I've calculated the average return for each of those two. The holding period return average is 3.25% for B, and for the index, 3.5%. Now we notice that if you look at the holding period of A, it varies from 10 to 6 to minus 8 to 10. So the idea is how much variation, how much does that differ from its average? And differing from the average gives us a feeling of, if there were absolutely no difference from the average, you'd have exactly average, and difference from the average is what we're calling risk, and we measure it by variance. So if I take the holding period return of A, subtract off the average return, I get the deviation from average. So 10 minus 450 is 550. 6 minus 450 is 150, etc. Now there's a minus sign. If we add these up, they'd sum to 0. To get rid of the minus sign, we square it. Later we'll undo the squaring by taking the square root. So 5.5 squared is 0.30%, 1.5% squared is 0.02%. If I add them up, I get the sum 2.19%. Now to divide it, we want to divide by n minus 1. We had 4 observations, so we're going to divide by n minus 1, which would be 4 minus 1, 3. We call this sample variance, as opposed to population variance, where you divide by n. So you're reducing the number because you're dealing with a sample. Obviously, it wouldn't be important if I had 1,000 observations where I divided by 1,000 or 999, it wouldn't matter. But with a small sample, it makes a difference. So 2.19% divided by 3 is a variance of 0.73%. The 0.73% is a squared number because we did the deviation squared. Now if we take the square root of that, we get 8.54, and the square root of the variance we call standard deviation. I put a .s to remind you that it's a standard deviation of a sample by dividing by n minus 1. If we go to the next slide, I'm going to do the same thing over again for B and the index, so we have a little more information about B and the index. So on the left-hand side, you see I did the calculations of the actual return minus the average, getting the deviations from average, squaring them, adding them up, and divide by 3. Gives me a variance of 0.38%. Again, taking the square root of that, we get back to standard deviation 6.13. Looking at the index, I repeated the exact same procedure, actual minus average. The deviations I squared, I sum them, divide by n minus 1. That gives me the variance. I take the square root of the variance, and I get standard deviation, which is 5.07. Now, if we wanted to compare A, B, and the index, we need a common way of doing it. And basically we're going to relate to return to risk. So there are two ways you could do this. Obviously you could divide return by risk or risk by return. The standard for the industry is to take the standard deviation and divide it by average or mean. So it's a risk per unit of return measure. So if we look at stock A, the standard deviation is 8.54. We divide it by 4.5 and we get a coefficient of variation of 1.9, meaning the risk is 1.9 times the size of the return. Do the same calculation, standard deviation divided by average for B, and for the index you see that for B it's 1.89. They're both about equally risky, even though the risk is smaller for B, so is the return. We look at the index, it's 1.45. The risk is about 1.45 times the return as opposed to 1.9. So the index is giving you more reward for the risk you're taking. The other two are more risky, let's say, than the industry average or index that we're using. Now we'd like to know how much is in common between the variation of stock A and B. So we're taking the deviation of A times the deviation of B. We call that product. So 5.5% times 5.75% gives me 0.316%. Again, repeat the deviation of A times the deviation of B. We call that product. We add it up and again divide by n minus 1, and we get the sample covariance. And the sample covariance is 4.32. It's not a really meaningful number by itself, but it's used a lot, and so we'll see it used later on in our calculations. I'm going to do the same kind of calculation for A with the index and B with the index. So I'm looking at the amount of covariation between A and the index. Now if we assume index has systematic risk, then we're talking about how much of A's variance is varying with the index, how much of A's variance is systematic risk. So I took A's deviation from the average, I took the deviation for the index, multiplied them together to get product, added them up, divided by 3. So the covariance of A with the index is 0.417%, and for B with the index is 0.205. Notice you're going to have two variables. It's a relationship between two things, A with B, A with I, B with I. So we'd like to know what percent of the total risk is related to systematic risk, and that's correlation. So we can think of correlation as the degree of similarity in the returns of stocks A and B, how similar they move over time. The correlation is simply the proportion of covariance of the risk to the total risk of A and B. So we can see it as like 20% of the total, 50% of the total. Obviously it can be 100% of the total. So to do the calculation, we take the covariance of A with B, divided by the total risk. The total risk is the standard deviation times the standard deviation of A times the standard deviation of B. Covariance, remember, is a squared number. So standard deviation of A times standard deviation of B is also a squared number. Going to putting in numbers, the covariance for A with B was 4.32% decimal. We had the standard deviation 8.54 times 6.13. This gives us a ratio of decimal 432 to decimal 524, which is about 82.4%. So there's risk in common between A and B, meaning that the returns that move are about 82.4% in common. And so that the rewards we're getting are very similar. They might be in the same industry, or somehow they're related. If we look at the correlation of A with the index and B with the index, we're really asking is how much the return is coming from the index, meaning how much of the return is reward for systematic risk. So again, you're taking the covariance of A with the index and you're dividing it by standard deviation A times the standard deviation of the index. We look down, we see the covariance is 4.17. We're dividing it by the product of the standard deviations, and it turns out that the correlation is 96.3, suggesting that 96.3 of the return is coming from systematic risk, and the remaining amount is coming from business risk. So most of that return is systematic, reward for systematic risk. We look at B with the index, the correlation is 66%, so it's a lot less return coming from the stock index, a lot less return is systematic risk. Reward or premium for systematic risk. So let's take a look at that beta measure. And the beta measure is simply the covariance divided by the variance of the index. I made a note that the variance of the index is the standard deviation of the index times the standard deviation of the index. So the beta for A is 1.62. We said in file that beta of 1 is exactly as risky as average. Greater than 1, like 1.62, is much more risky than average. A beta of 0.8, like for B, is about 80% as risky as average. So you can see that they're vastly different relatively. All it means is when the index goes up, A moves by a lot, B moves by much less. When the market goes down, likewise, A moves down by a lot, B moves down by less. So that ends our chapter with risk measures. When we go into the next file, we'll actually be downloading data and repeating the process.